Till now about corona loss, what we have discussed is about the descriptive critical voltage, the particular voltage level above which the corona loss starts to occur. For the descriptive critical voltage, we have seen the formula and how the critical voltage value is taken from that formula for single phase and three phase. Next one is the visual critical voltage. In the disruptive critical voltage, the potential difference V at the particular point in which the corona loss acts for this is for the single phase and this is for the three phase. Similarly, visual critical voltage, what is the value for the single phase and three phase? We are going to see the formula. And the disruptive critical voltage deals with the roughness factor. In visual critical voltage, it deals with the surface factor m naught. What is visual critical voltages? When the corona is visually visualizes. What is the critical voltage for that visualization of the corona? My experimental investigations have revealed that visual corona does not occur when the electric intensity become equal to the critical value E naught, but starts higher than the value of EV. When the critical value goes behind or beyond EV, then the visual critical voltage can occur. At this point, the dielectric breakdown of ARS occur. Dielectric breakdown occurs. In other words, for visual critical voltage, dielectric breakdown of AR is needed. So the dielectric breakdown voltage for the visual corona is EV is equal to 3 into 10 to the power 6 divided by root 2 into intensity into MV. MV is the surface factor, and for the critical voltage, it should be the dielectric breakdown should be occurred and it will be above the normal critical voltage value E naught. So 1 plus 0.03 into root of del into R. R is the radius of the conductor and the unit is voltage per meter. Similarly, when calculating so this is the potential difference. For calculating the voltage at the particular point for the visual corona is 6 into 10 to the power 6 divided by root 2 into del mv into r 1 plus 0. Same value which is a constant which relates the density of the air and the barometric pressure P, as we have discussed in the descriptive critical voltage, del into r into ln of d by r. D is the distance, r is the radius. This is for the single phase. When we are going for the three phase, the only parameter that is going to change is q by 2 pi epsilon naught. So 2 will get cancelled. So the value will be 3 into 10 to the power 6 divided by root 2 del into surface factor into radius of the conductor plus the visual critical constant 1 plus 0.03 into root of del into r ln. Here it is D equivalent which has 3 conductors. So D equivalent divided by r. So this is the visual critical voltage value for the single phase and three phase. The next topic we are going to discuss about the corona losses. The voltage at a particular point, that is 30 kV per centimeter, is the point critical voltage value where the corona is occur. Where the stage of corona occurs. Due to that corona, what are the losses is that the first one is the efficiency. Because to ionize the air around the surface, it needs some power from the line. So that power is dissipated. So the efficiency of the total transmission system is reduced. If the corona is not monitored and it is or reduced, the total efficiency is reduced. But it not affect the regulation. So what are the corona losses and what are the factors that is affecting the corona losses is the next topic we are going to discuss about. Factors affecting the corona losses. First one is the frequency. There is a formula called the peak formula. From this peak formula, we can justify or we can relate that the corona loss is directly proportional to the frequency. So the peak formula is PC is equal to 243.5 plus F plus 25 divided by del into root of R by D into V minus Vd the whole square into 10 to the power minus kilowatt per kilometer per phase. So this is the peak peak formula, which is directly proportional to where the power loss in the power loss due to the corona is directly proportional to the frequency, and also the difference between the critical and the normal operating voltage condition. So in order to obtain this and to maintain the to eliminate the corona loss, there should be a proper V by Vd ratio. So the V by Vd ratio should be greater than 1.8. So if it is greater than 1.8, it will give the better results for the reduction of corona. So the first factor that is affecting the corona loss is the frequency, and the second one is the effect of the system voltage. As the system voltage increases, the corona loss is also increases. We have discussed when we are discussing what is corona and what is the major factor for the corona for the 100 kVA line. So the voltage at a particular centimeter with the voltage gradient increases if the system voltage increases. So the system voltage and the electric field, they both are interdependent. So the electric field governs the corona. So the system voltage is directly proportional to the corona loss. Third one is the conductivity of the air, and fourth one is the density of the air. These two were directly proportional to the corona loss. Since the conductivity of the air increases, more ionization will take place. If the ionization increases, and the electric field intensity will increase. With increase in electric field intensity, the losses will increases. And the density of the air. So the conductivity and density, these two plays a major factor, the atmospheric factor of the landscape, that is at the sea level and above the sea level. And above the sea level, the density of air is high, so the corona loss is also high, and the conductivity of air is also high in the hilly regions. And the fifth one is the effect of rain and dust. Because of the rain and dust, if they are placed in the conductor, they used to increase the corona losses. So if we increase the diameter, the effect of rain and the dust will not affect the corona losses. And the next one is the conductor radius, which is related to the effect of rain and dust. Higher the conductor radius means lesser the surface field intensity, and hence reduced corona losses. Higher the conductor area, lesser the corona losses, because the surface field intensity, if the conductor area is high, the surface field intensity will be lesser, so the corona loss is lesser. When we compare to normal copper conductor, ACSR conductor will have the reduced corona losses. So this type of conductor is preferred to reduce the corona losses. So these are the factors that is affecting the corona losses. Accounting these factors, we have to determine what will be the conductor radius, density, and other parameters which is affecting is also the atmospheric pressure and also the density. Accounting to this, we have to decide some factor which to reduce the corona loss and to increase the efficiency of the transmission system. So in third unit, it's a very small unit, and we have discussed about what is the history of the HVDC transmission, why we are going for HVDC, and what are the types of DC links that is we are used currently, and how those DC links are evolved. From 1954 it is monopolar, 1961 it is bipolar, and now they are using homopolar DC links. And after that, the corona loss, and two type of voltages, descriptive voltage and visual corona voltage, visual critical voltage. So these two type of voltages have been discussed. Then the factors that is affecting the corona, that are the mainly to 6 to 7 points that is being discussed. What are the factors that is affecting the corona, and what the factor will be higher, and how the corona losses will be, and what is corona loss, and mainly what it is affecting is the efficiency of the transmission line, but it's not affecting the voltage regulation. In order to improvise the efficiency, the factors which is affecting the corona loss should be eliminated. So that's all for the unit 3. So the next unit will be your about the cables and insulators.